Yeah, again, my name is John Willis. I'm a team lead with the AI engineering team here at Vector. So I'm excited to share a little bit about VectorLM, a package that we recently released for the Vector community. This will be a bit of a change of pace, something a little bit more applied, but hopefully, of interest to the community. Before I get into it, I'll just start with a few words about Vector AI engineering. I don't think that everyone has necessarily worked with us or is familiar with us, but we're the professional engineering staff here at Vector. We're a team consisting of machine learning engineers, software engineers, applied scientists, and product and program management staff. And we're now over 30 strong. And what we're here always looking for is opportunities to better support and collaborate with the research community, you guys. And so that's all what VectorLM is really about. I don't think this will be much of a surprise to most of the people in the room. Some of the trends that we've seen over the last few years in language modeling, particularly in the pre-training space, is that there's large compute requirements. Looking at 500 to 1,000 minimum A100s or H100s for these types of workloads with long training schedules and high cost associated with them. But there's a whole host of other workflows from continued pre-training for things like domain adaptation, instruction fine-tuning, DPO, RLHF, a wide variety of other workloads of interest that are far more compute and cost efficient. And so that's really what we've been looking at for the last little while. So in terms of compute, what do we have available at Vector? This is probably review again for lots of you. But our cluster is about 1,000 accelerators of a variety of different generations. At the high end, we have about 50 A100s, 200 A40s, about 250 RTX 6000s, about 500 T4s. And so looking at the communication backing those accelerators, just looking at the A100 partition, we have fairly slow node-to-node communication. So remember that we have 4 A100s per node. And so the communication between those nodes is pretty slow at about 50 gigabit per second. But we do have relatively fast communication within a node. So that's sort of an important thing to remember moving forward. Inter-node communication slow, communication within a node reasonably quick. So that's the constraints that we're working with. So what is VectorLM? It's a package that we open source. It's available on the Vector GitHub for anybody to use. And the intention is it's a starting point to sort of jumpstart your research. So we provide optimized workflows for vector compute for a variety of common workflows. To date, supervised fine-tuning, instruction fine-tuning has really been what we focused on. Full fine-tuning of a variety of different models, the full Llama family as well as Mistral. And so what's available is you've got everything out of the box. You've got the Slurm scripts. You've got examples to start working on vector compute. And it's been optimized for that compute. And that's what I'll spend a bit of time talking about today. Some of the design decisions that went into VectorLM, as well as some of the under the hood optimizations that make it reasonably efficient. And so I'll present that sort of through the case study of a collaboration with one of the Vector faculty, Professor Rahul Krishnan, where we were working with him to explore domain adaptation and fine-tuning of language models for medical and clinical tasks, with an ultimate goal of trying to deploy something with one of our health partners. From a modeling perspective, we're very focused in this work and up till now on full fine-tuning of models in and around sort of the 7 to 13 billion parameter range. And the data sets that we've been working with and that we'll sort of look at in this talk is a novel data set compiled by one of Rahul's students, which is medical textbooks and journals that we'll call MDPI, MTB. We've also been working with a QA data set That's a sort of a semi-synthetic data set generated from seed medical facts. In total, this looks or is about 1 billion tokens. So not a massive data set by any means, especially in comparison to pre-training, but not small nonetheless. Okay. So this is sort of just a visualization of these workflows. We're, of course, building on the pre-training that's done by those who are open sourcing those pre-trained models. So Meta or Mistral with those really compute-intensive pre-training stages. But we're exploring the fine-tuning phase, instruct tuning phase, much more compute-efficient workflows building on those open source artifacts. And so what are the challenges with this? Well, the first thing that you maybe want to ask yourself is how much compute or memory do we actually need to do this? So making a sort of a reasonable assumption of mixed precision training, which is pretty common, you're looking about 6 bytes per parameter in terms of model weights. So that's your master copy, or sorry, your master weights in your copy. In terms of gradients, 2 bytes per parameter. Optimizer state, assuming we're using Atom, you're looking at another 8 bytes per parameter. You've got activations and buffers on top of that, bringing to make a reasonable assumption of about 16 bytes per parameter. So what does this look like in practice for that 7 billion parameter model? We're now over 100 gigabytes of GPU memory. For 13 billion, we're over 200. And that 70 billion parameter model, we're over 1,000 gigabytes of memory, which puts us in a bit of a tricky situation, given that we just saw that our best card, our A100, only has about 80 gigabytes of memory. So where do we go from here? We need to explore some sort of parallelization strategy. I won't get into this in too much detail in this talk, but you might be familiar with some of these techniques. There's data parallelism where your model is duplicated across GPUs. There's tensor parallelism where you're splitting operators across GPUs. Pipeline parallelism where you're splitting layer-wise across GPUs. There's all kinds of different approaches to this. But sort of what you need to know is that there's libraries out there that will help abstract some of these things away from you. A number of libraries that range from sort of more flexible libraries like DeepSpeed or fully sharded data parallel FSDP to more complex but perhaps more performant libraries like Megatron LLM. In terms of the direction that we took, we decided to build on FSDP. It's torch native. It implements a zero-based sharding strategy, which is attractive in a research environment, especially if we're targeting something that's usable by end users that don't have a lot of distributed computing experience. It makes fewer assumptions about or requires the end user to make fewer assumptions about the model, and is a little bit easier to sort of plug and play with new models at will. But sort of a key thing to keep in mind, the way that it implements parallelization is you can sort of think about it as taking a vertical shard of your model and placing it on each of your data parallel workers. And as you're computing your forward and backwards pass in the model, you're communicating between all those workers, gathering those weights as needed, computing your forward pass or backward pass, and then freeing that memory as you go. So it facilitates sort of this parallelization, but has a communication overhead. Okay, so now that we've selected a library, we have our data set, we can start with our first training attempt. So in this case, it's continued pre-training setting. Our data set is MDPI, MTB. We've selected FSDP as a library backing this. We're training Llama 2 7 billion, and we've allocated 2 of our A100 nodes. So 8 A100s in total. How did it go? Really poorly. So in terms of training throughput, 1,400 tokens per second. to contextualize that a little bit, given that billion token data set that we're operating with, we're now looking at over 8 days per epoch to train on that data set. So not great. So we look at what optimizations can we implement. If we remember the vector cluster communication that we looked at the start of the talk, we'll remember that we have slow internode communication, so only about 50 gigabit per second internode, but we do have fast communication within a node. So what we identified was that there was the communication of the communication of overhead of FSDP was creating a pretty significant throughput bottleneck. So sort of the takeaway here is that more accelerators and more GPUs are not necessarily better if you don't have the communication available to support it. So the naive solution here is let's reduce training to a single node and see what that looks like. We drop down from our 2-node allocation to a single node allocation to just 4 A100s. What's the impact here? We remove that internode communication dependency, and we see our training throughput increase quite dramatically up to about 8,000 tokens per second. So that cuts total training time down from over 8 days per epoch down to about a day and a half per epoch. But we didn't stop there. There's other optimizations that we could implement. This one is probably well known to many in the room, and maybe sort of the next place to look, flash attention. Again, I won't get into sort of the specifics of the algorithm, but it's an IO-aware algorithm for attention computation. And again, we saw a pretty significant performance gain implementing this. So comparing that run without flash attention, again, on one node of A100s, we're at about 8,000 tokens per second. Implementing flash attention, we jump up to about 16,000 tokens per second. So that's a 2x increase in performance, bringing that total training time down to under a day to about 0.7 days per epoch. But we've got half of our compute allocation now sitting idle. So what can we do with that? The solution that we implemented was a hybrid FSDP solution. The objective being to reduce that communication overhead across nodes, keep the communication within a node. And so you can think of this as implementing FSDP within a node, but more sort of traditional data parallelism across nodes. So again, we're sitting at about 16,000 tokens per second on one node of A100s. Implementing hybrid FSDP, we're now up to about 30,000 tokens per second, bringing that total training time again down to about 0.38 days per epoch. So quite a dramatic change, and also something that we can now scale to more nodes. If we want 3 nodes, if we want 4 nodes, this is now a scalable solution if we want to throw more compute at it. In terms of some other optimizations that are implemented, Tensor Cores are a specialized compute unit that's available in more recent NVIDIA GPUs to facilitate things like mixed precision training. But there are some gotchas in terms of how tensors need to be shaped in order to take advantage of them. So that's implemented, as well as activation checkpointing, which you can in our case, didn't really increase our throughput, but it allowed us to increase our batch size. So there's different things that you can take advantage of there as well. So in terms of high-level takeaways, make sure that you understand your compute environment. Make sure that you explore the hardware and software optimizations that are available. They make a difference. The communication is as important as the accelerator. So just because you have a whole bunch of accelerators available, if you aren't thinking about how they're communicating as you're scaling these types of workloads, you're going to run into issues. And so again, just looking at some of these high-level metrics, this is a direct comparison of sort of the naive implementation on 2 nodes of A100s. We went from 1,400 tokens per second to 30,000, 8 days per epoch down to well under half a day. about a 22x increase in performance. And so, this is now open source and available on the Vector GitHub for all of you to use and to build on. And so in terms of next steps, we're really looking for feedback from the community on what you might like to see built into this package. But some of the things that we've identified are maybe an A40 optimized workload. So can we make this available on some of the smaller cards? Parameter efficient fine tuning. So perhaps like LoRa directly implemented in VectorLM. DPO, there's some interest in exploring mixtures of experts more directly as well. So, please reach out for support or collaboration. Really looking for feedback. Happy to meet with you, look at your own workflows, how they could be worked into VectorLM. Provide an onboarding session if that's helpful for VectorLM. Really here to sort of support you if you see value in building on top of VectorLM. So you can reach out to me again, John Willis, Vector Slack. Send me an email anytime. Adil is also did actually a lot of the development here, so a lot of credit goes to him. Similarly, you can reach out to him on Vector Slack, Vector email anytime. So yeah, that's sort of all that I have today, but happy to take any questions, and I'll be around for the rest of the afternoon if anybody's looking to chat. Yep.
So as of now, you don't support the pre-training, right? And do you have any plan to add the pre-training stage as well? And if not, in comparison to NVIDIA Megatron LM package, for example, do you know how much efficient that package is in vector, basically system in general?
Yeah, it's a good question. So in terms of pre-training, this supports continued pre-training. So, there's really, if you have the compute available, then you could use this. The communication over, internode communication effectively restricts us to like about 13 billion really efficient training. So yeah, if you had the compute available, there's no reason you couldn't do pre-training with this if you wanted to. In terms of Megatron LM, we haven't looked at it or we haven't done much benchmarking with it just because the gains that you see are more apparent at larger scales that we're not necessarily operating at. So it comes with a lot more load on the user. You're now, instead of sort of handing it off to FSDP to figure out how you're going to shard your model, you now need to think about that in advance and manually configure that. So there is a lot more expected of the end user with a library like that.
Yep. Have you benchmarked what is the hardware flops utilization?
No. So that's something that we'd like to do, and are sort of actually working on building real profiling directly into VectorLM, so that it's really simple if you were using it in your own workflows to sort of profile as well. So that's something that should have been on the roadmap there. That's something that we're really interested in, but not something that we've done yet.
And also, I heard at some point you were debating between JAX versus PyTorch. Is that you finally decide to go with PyTorch?
Yeah, we've settled on PyTorch. It's pretty widely used, and most of, I know not all of the research community is PyTorch, but quite a bit. Yeah, so that seemed like the direction.